Okay, so yeah, so this so Mahan asked me to talk about SLE. So unlike the others in this series, by the way, I am not at all an expert in this or anything. So some of you may know more. Anyway, so I'll probably speak for 3 weeks or something. I mean, 3 lectures. So my plan is to introduce SLE and basics of SLE. Okay, so one possibility is to start with the motivations and so on. So I thought usually one always starts like that. I got a bit bored. So I thought that I will anyway introduce the objects first and then give the motivations afterwards, maybe in the next lecture. So basically SLE are some random curves in the plane, and they describe scaling limits of many random curves, discrete random curves that occur in probability. Some of them proved, many of them not proved yet. So what are these random curves and why were they defined? How are they defined and why, etc. So this is the goal. So today I thought I'll just introduce Lowness differential equation and so on. Not much give motivation of probability, but we'll see that later. Okay, so at any time just stop me. Okay, whatever my plan is, it doesn't matter. So you can stop me at any time and ask questions. Okay, so and don't ask in chat, I don't see it. So if you want, so you can unmute yourself and ask. By the way, you are able to hear me, right? Okay. Okay. Okay, so what is this Lowness differential equation? So let me start with the differential equation straight away. So here is the differential equation, x dot of t equal to 2 over x of t minus u of t. So this is for time positive, and here u is something, is a curve, given curve. So means it's continuous, it's some continuous function. So we will always start with u0 equal to 0, but that is optional. So you can start this, you can take this differential equation, solve it from any point. So we will be solving from points not necessarily in the real line, but in fact mostly in the upper half plane. So upper half plane is okay. So Z is somewhere here, and we consider this differential equation starting from some point. So sometimes we also take Z in R also, but for now you think of Z only in the upper half plane. So what happens? So this solution will, of course, you can solve it up to a point. So this is standard differential equations business, tells you that you can solve the says that solution exists up to some time, up to a time which depends on, let's say, Z in the following way. It is the, as long as the vector field which is defining it is not 0, it's okay. I mean, doesn't blow up, it is okay. So it is the infimum of times when x of t is equal to u of t. Okay, so u is actually somewhere on the real line. Okay, so let's say is here and then it is moving like this. Okay, so as it moves, this z will flow, and it flows something like this. It may happen that at some point it comes and it meets ut. At that point, it ceases to make sense, and we cannot define we cannot develop the differential equation anymore. That point, but it may also happen that this tz is infinity also. This could be infinity also. But you can define this xt up to that point. Okay, So this is clear from standard ODE theory. And so this solution will be denoted, this solution we will denote GT of Z. Okay. So we'll make Z the variable here. Okay. As a function of the initial condition, this is GT of Z. It is only defined up to this time. It's understood whenever I write this. Okay. And what else can we say about this solution? Okay, so this, so if you look at this, this is the vector field here, a time-dependent vector field. V of t comma z is, let me call it t comma zeta, is 2 over zeta minus u of t. So this vector field, you see, is the solutions. What is the dependence of solutions of ODEs on the initial condition? Again, it is standard theory that it is as good as the vector field essentially. Okay, so for basic theory, you usually assume that this is Lipschitz to get existence of the solutions. But if it is nicer, then the solution as a function of the initial condition will be almost exactly as nice. So what we see also is that Z going to GT of Z is holomorphic. Of course, as long as t is less than tz. If t is less than tz, then nearby points will also have not yet hit this explosion time, and then GT will be holomorphic in the neighborhood of that. So that is also coming from here. If you want, in fact, you can just differentiate under this. So what we have is GT of Z. Let me denote the dot denotes the time derivative. Okay, by the way, this dot is time derivative always, is 2 over GT of Z minus UT. And you can just keep differentiating under with respect to Z. So GT dash will be satisfying this equation. Times 2 GT dot of Z, which again is you can write from here and so on. Right? So have I done the right thing? Sorry. So GT, no, I wanted to differentiate with respect to Z. So what did I write here? No. So if I differentiate with respect to Z, I get, oh, sorry. I just get, and so on. You can, so it's holomorphic in this. So this is actually, this is the Lohner differential equation, by the way. So this is what is called Lohner's differential equation. And what other properties do we have? So let me just make some observations and then I'll give examples. So what other thing can we see about these things? So one of them is, as I have written here, it will be somewhat important or maybe not so much, but if you look at the imaginary part of this, again, you can push it through the derivative here, imaginary part of GT of Z. If you push it through here, you will see that it is and then what you get is 2 times minus 2 times imaginary part of GT of Z. Because I have written it as GT bar of Z, so it is negative. So it is negative. So all the flow lines are downwards actually. The imaginary parts are going down. Wherever you start in the upper half plane, all the flow lines are pointed downwards. The real part can go left or right, but the imaginary part is always going down. That's one of the properties of this equation. For this reason, also, if you look at the reverse flow, if you look at the reverse flow, what is reverse flow will satisfy, let's call the solutions Ft of Z, suppose. What is the reverse flow? It is just the negative. At every point, the vector field is pointing in the negative of this direction. It is minus 2 over ft of z minus ut. For this, the flow lines will be pointing upwards, right? Because this is just the reversal of that. And so the flow lines point upward, and so they are well defined for all time. They will never hit ut. U is on the real line. So if you start, so this hence defined for all time. Okay, so that is another point. Okay, so what else do I have about this? Right. Okay. So now, so to define SLE, to define, sorry, not SLE, but so these things. Yeah, maybe I should give an example here. Maybe let me just give an example first. Very simple example. So take ut equal to 0 for all t. So then what we have here is that, so ut is 0. So what we have is gt dot of z is over gt of z, which you can solve easily and write gt of z is so at least formally, if you differentiate it, you get that it is 2 over gt of z. But one should be careful what this means, the square root here in the complex plane. So what we have here is, so let's say z is in the upper half plane. You apply z square, then you get everything except the negative. So you'll get complex plane minus, sorry, what did I do? Yeah, so if you, yeah, you get complex plane minus the positive real axis, right? And you shift it by 40 and then take square root. So for example, so if z is somewhere here, so let's say z is here, so z square is here, then you add another plus 40. So it will move to the right. And then you take the square root, which is again unwrapping it to the upper half one. Okay, so where can the problem be? So this is actually, so if you look at this one, so gt of z is not defined. It is here. Well defined if z square plus 40 is not negative. Okay, so that's where we will have problems. So if you have z square plus 40 negative, then you cannot take the square root. So what that means is that so if in the upper half plane, there is a slit from 0 to 2 times I square root t. If z belongs here, then when you square it, z square will be on the negative axis, and then when you add 40 and then take square root, it will not exist actually. So the gt of z is well defined outside of this. Okay, so what gt does is, gt is well defined on this region and it maps it to the upper half plane. That's what it does. Or if you want to, okay, so maybe since I didn't say it that way, another way to say it is, if you start from any, so maybe I say it in another way. If you start this gt of z, with z in the upper half plane, then you get this one. So tz is infinity unless z is on the imaginary axis. Okay, so you solve this equation. Unless z is on the imaginary axis, you will it will be the flow line is well defined for all time. You can just see that it's pointing downwards. And first, if you are at Iy, then the time at which it gets absorbed is exactly defined by this, which is when 40 equal to y square equal to 40. So it is something like, I think y by 2 or something like that. Is that right? Okay, so something like this. So these points, they are flowing down only up to a time t. So if a point is on the imaginary axis, it will get absorbed at some time. Otherwise, it will never get absorbed. So this slit is all those that were absorbed up to time t. Okay. So that is the general definition I want to make. So we have this differential equation from any starting point. It is well defined up to a time. And what we want to consider is those things which are not which are observed up to time t, by time t. So define all z in the upper half plane which are absorbed by time t, and ht will be the remaining, the complement of that in case in the upper half plane. So in this case, this black slit is the part that was observed up to time t, and everything outside is there. So the point I want to make now is that these GTs, we already know they are holomorphic and they are well defined on HT only, right? Because for Z in KT, GT of Z is not well defined. These are the Zs for which GT ceased to exist by this time. So GT is defined only on this part. So the claim here is that GT is a map from HT to the upper half plane. It is a conformal bijection actually. So it is like it is the Riemann map from this domain H/KT to the whole of the upper half plane. So it's actually more or less we have the proof. We know that it is holomorphic, and flow lines don't meet anyway. So GT of Zs are actually, if you start at two different Z, they are flow lines of the differential equation. So they never meet. So that is why injectivity flow lines don't meet. I mean, so, and why is it surjective? You can just run the reverse flow. So if you want to see what gets mapped to this by, so if W is here, and you want to look at GT inverse of W, you just run the reverse flow. In the reverse flow, it will go somewhere. So this FT of W is going to be GT inverse of W. It's the point where if you start from there and run up to time t, you will come to W. So every point W has a flow line going up for time t. It goes on forever. Therefore, it is actually also surjective. So GT is a holomorphic map from this domain to H. It is holomorphic, injective, surjective. So this is a conformal bijection. So any questions? I mean, I don't know whether I'm going too fast or something.
Yeah, so Manju, one quick question about the motivation for this particular thing. So is it the, I mean, you started off with the differential equation and then you're giving a geometric interpretation as a uniformization of the upper half plane with, say, a slit which is progressing along the y-axis.
This particular example. In general, KT can be more complicated.
Correct. Correct. So, I mean, why would one consider such a differential equation in any case? I mean, that's, I think, I mean, what is the motivation for, I mean, is this the motivation and then you formulate it in the differential equation? Are you doing the reverse? Are you doing some
I am
reverse
sort of, so Lohner did it in the reverse, actually.
Okay.
So I was planning to tell that afterwards.
Okay.
So Lona was starting in the reverse way. So since you ask it now, let me just quickly say it, but I wanted to say it later. So what Lona wanted to study was to take, let's say, a slit map. Okay, so you have a curve, gamma, and then for every t, he considered a map, let's call it GT, is the conformal map from upper half plane minus gamma 0 t. So let's say gamma is a curve which starts at 0 and keeps going up. If you remove the initial part, then there is a conformal map which maps it to the upper half plane. There's a choice to be made. I have not yet made clear. So there's the conformal map is not unique. There is a normalization involved, which I have to explain still. But modulo that, there is a, let's say there is a conformal map. And then he studied, and then, so this is what Lohner did. Start with gamma.
Is the normalization infinity goes to infinity at t goes to 0 or something like that? I mean, gamma of t.
Yeah, infinity goes to infinity, but one more point. So there are three. There's
yeah. Gamma of t. So gamma of t goes to 0. Is that the point?
No, gamma is given to us. Gamma is given to us. No,
when you uniformize,
starts from here. Sorry, gamma should be thought of as starting from here.
Correct.
Gamma 0 is 0.
Yeah.
Gamma 0 is 0.
Yeah. No, in the uniformization, are you sending gamma of t, the point gamma of t, because you're going to slit, right?
Yes.
So this gamma of going to be a point on the boundary of a conformal upper plane. Are you sending that to the origin of?
No. Okay, the normalization here is that. So you send infinity to infinity, and then GT of Z looks like some AZ plus B plus C over Z plus D over Z square plus so on at infinity. Okay. So for those who are not familiar with this, let me just quickly explain that if you look at it in, so look at the point infinity, which is on the boundary of the upper half plane, also on the boundary of this domain. So we take a conformal map which sends that boundary point to the boundary point, infinity to infinity. Also, this conformal map by just Schwarz reflection, you can extend to the complement of this and its image. Therefore, it is defined in a neighborhood of infinity. All I want to say is that GT is because this is a compact set, a neighborhood of infinity is away from all this. So you can extend it across the real line by reflection, and it has a power series expansion like this. So we have already used one parameter to send infinity to infinity. What we do is we also make A to be 1 and B to be 0. So this is what is done.
Okay.
So is this what is called the hydrodynamic normalization?
Yes. So this is called hydrodynamic normalization. I don't know why that word is used at all, but
so Manju, this is what we call, the capacity. Okay, so for capacity, actually, we will keep it to be A of t, right?
Sorry.
So A equals 1 gives 1 capacity, right?
Yeah. So the coefficient of Z.
So let me call this number A of t.
Yes, A of t. Sorry, 1 over Z. Yeah.
Plus lower order terms. So let me just write it like this. So I already did. So Z. Okay, let me just write it again. So let's write it as Z plus A of t over Z plus big O of 1 by Z square as Z goes to infinity. Okay. So this is how it's normalized, and you can reparameterize. If you reparameterize gamma, this A will just get reparameterized. That's all. So you can reparameterize.
So A of t is twice the capacity of the curve, or just the capacity?
So maybe I'll call it 2 times here. Yeah. So well, okay. So that was A of t, whatever it was. That is 2 times the. So this A of t is something, we can normalize it so that it is 2t. One can show by just Schwarz's lemma implies that A of t is increasing and continuous. Okay, increasing comes from Schwarz's lemma. It's also continuous. Okay, that comes from something. I don't want to worry about it. So you can reparameterize so that it is 2 times t. And then you get, so this is, okay, so you can do this. And then Lohner showed that once you do this.
Sorry, Manju, just one thing. The continuity of AT should be some kind of continuity statement for Riemann maps, right?
Yes, yes. So this gamma is continuous. And yeah, what is, let me just see. Yeah, it's almost like, yeah, it's right. When you change this gamma slightly, then it's the domain is only changed slightly. You can show that GT and GT plus H are very close to each other. And this is some kind of a derivative at infinity, and they will also be close. Yes, that's how you get the continuity.
So what, maybe parameterized Riemann mapping theorem or something like that? Or
yeah, it should be some parameterized Riemann mapping theorem. Yeah.
You can, I mean, this is also, if you want the usual category convergence, I mean, so when domains, so there's a question of if.
Yeah.
That's what it is. Category kernel moves continuously. Yeah. So if the domain move continuously in the category metric, right?
Okay. Yeah. That's so. Okay. Yeah. So what Lohner started with was so if you forget all this, so what I'm answering is Mahan's question. The motivation started like this. What Lohner started with was a curve. Then he defined these GTs, which are defined for every t as a conformal map from H/gamma 0 t to upper half plane with this normalization. And you also reparameterize so that normalization is 2t. Then he showed that GT satisfies this equation. GT dot of Z is 2 over GT of Z minus UT, where U of t, so this is what Mahan was asking. So one thing is, now where will this point go? So it's a general thing about conformal maps that, so what happens to the conformal map? So G is defined on this conformal map. What happens when you approach a boundary point? So let me just assert this point. When you approach a nice boundary point like this, then GT of Z will approach a boundary point on the real line. Similarly, when you approach a point like this, it will approach some point on the real line. So so whenever you approach a point on the boundary, the corresponding image will approach a point on the boundary. However, these 2 points are very different in terms of the conformal map. So if you look at this point, you approach it from the other side, then it may go to some completely different point. In fact, it will go to a different point. So the way to think of it is, if you want a better way, one way, if you haven't seen this type of thing, a good way is to think of this slit as some slightly widened slit. So now you have a boundary and you see that this boundary point is rather far from this boundary point in some sense. So they will actually be very different. However, at the tip, there's only one limit. There's only one way to approach it. There's no right side and left side. And at the tip, there will be a unique point, and that this is gamma of t, and that will go to some point u of t. The unique limit as Z approaches gamma of t. So that is this ut. So okay, actually Lohner didn't ever write this particular differential equation. So if I have to be a bit more precise, then I have to say what he did. He didn't do this either. But okay, is this okay? I mean, so what we are doing is we are kind of starting reverse in this direction. Anyway, G0, by the way, you also notice that G0 is just the gamma is not there. I mean, so G0 is the identity map, and so G0 of Z is Z. So what we did was to start in the reverse direction. I just wrote down these differential equations. G0 of Z is Z, and GT of Z satisfies this differential equation. And that's how I am starting. Okay. Is
So
that
just so this probably explains why in the case when the UT is always 0, you have a symmetric picture. The tip is always corresponding to the origin. So your curve must be vertical just so that the left and right are symmetric. So the tip is always at the origin, right?
True, but I have not said that thing is a curve. I mean, yeah, in a way,
Right,
generally
right.
what happens is this can be complicated sets. When we start in the reverse, so Lovna was not interested in that. He was starting with a curve and looking at and then there is a UT. But from you, when you go back, you don't always get a curve. This is going to be one of the issues that we will talk about a little bit.
I see.
So it can be, I mean, it can be somewhat complicated sets also. Yeah. Any other questions? So let me just say that actually Lovna never wrote this. Since I am saying this much, I may as well say that Lovna never wrote this one. Actually, what Lovna wrote was, he did not consider this. Okay. One superficial change I will make because it's hard for me to transfer the differential equation to the picture. So this is just a superficial change. You look at the disk instead of the upper half plane, but that is of course not a serious point. So, and instead of a curve starting from the origin, you look at a curve starting from let's say 1. Okay. Again, you can do exactly the same. So if you have time t, let's say this is gamma of t, then you can map it by gt to again the disk. Okay. So this is the Riemann map from the disk minus gamma of 0 to t to the whole disk. Okay. But the key difference is in the normalization. Normalization is not at a boundary point. If you just normalize this at -1 and some things, then you would basically get an image of whatever we have said here. But that's not what Lovna did. Lovna normalized it at the origin, at an interior point. So this is normalized so that GT of 0 is 0 and GT dash of 0 is positive. Okay. Here you will see that Schwarz lemma in the usual form is very clear that when gamma increases, this domain becomes smaller. So GT, in fact, this is, you see that this is decreasing and continuous for the same other reasons that we mentioned a moment ago. So you parameterize so that the derivative at the origin is actually e to the minus t. This is the normalization they pick. I don't know if it is e to the minus 2t or e to the minus t, but let me just say it is e to the minus t. And what Lovna showed was then it satisfies a differential equation. What is that actually? One second, give me a moment. Oh, sorry. So the equation, yeah, let me write for the reverse equation. So you can write for GT also, but you can also write for the forward. In both cases, we can do the same way. Ft equal to GT inverse. So Ft will be just the reverse map. Satisfies Ft dot of Z is minus Z Ft dash of Z times something. I think you get some lambda t plus No, actually, sorry. Let me just check this. It is, what is the equation? Right, yeah, it is actually correct. Minus z ft dash of z lambda t plus, sorry, not ft of z, but just z. Where again lambda of t is the image of the tip, okay, but that will now come to the boundary. Lambda of t is gt of gamma of t, which belongs to the boundary of the unit circle. It has absolute value 1. So ft, I have written here the different, you can write the differential equation for gt, but it is also just as good. Yeah, so and why okay, so this is the equation he wrote. Lovner never wrote this. In fact, I don't know if anybody ever considered this boundary normalization still SLE. So these are called now in SLE literature, these are called chordal versions, and these things will be called radial, depending on whether your normalization is an interior point or a boundary point. They'll be chordal or radial. But this radial one, why did Lovner look at this actually? So the point, first there was a specific problem for which reason he looked at it, which was the coefficient problem, the Bieber-Bach conjecture at that time. So but the main point is this. The main point here was that you can approximate. So point 1 for Lovner was can approximate Riemann map from any domain, any simply connected domain to disk via this type of slit maps. What I mean is disk minus a slit map is disk minus a curve to disk. You can approximate anything by this. How? It seems crazy. It doesn't seem possible, but at least, okay. So I should maybe here I'll say bounded. The unbounded ones can be approximated by bounded ones. So let's take a bounded simply connected domain. Then you can always scale it, translate it, and assume it's a part of the unit disk. So let's say your domain is some. So let's say this is omega, interior of this, and I assume that 0 is inside. So any bounded domain you can scale and translate, and doing it inside the unit disk like this with 0 contained is an interior point, okay? So now how do you approximate it by a slit map? You can start at 1. So let me choose a different color. So let me start at 1. Take a curve which goes like this, so starts at 1, goes and hits this, and then traces the boundary. Like this. And at the end, it meets it, okay? So this is my curve. The point is that these maps, GT, so let's say at the point that it comes back, so let's say G is the conformal map from omega to disk, normalized so that G0 is 0 and G dash 0 is positive. Now you look at GT, so this gamma T is defined for, let's say, 0 less than equal to T less than equal to capital T. So you have normalized it with all this radial parameterization, e to the minus t and so on. But at some finite time, it will come and hit here, right? That is my capital T. This is the time when gamma of t is actually well, what? Okay. Okay, you understand what it is. It is this is the first time gamma ceases to be simple. By the way, you don't have to worry. Okay, I wrote a Jordan domain here, but again, that's an approximation question. If you have some other somewhat not such a nice simply connected domain, you can still approximate it by a Jordan domain and do all this. So you can, but the point here, and this is a point that may be not familiar to those who are in the probability side if they haven't seen it before, but complex analysts know it, that this thing, it may seem that something discontinuous is happening at this time, but no, this GT approaches G uniformly on compact subsets of omega as T approaches capital T. So in other words, you can approximate your Riemann map by these type of maps, and in every nice sense. Okay, so for example, all the coefficients at the origin will converge. So as a consequence, all coefficients if you write GT of Z as, let's say, Bn of T, Z to the N, then, and G of, and let's say G has a power series expansion. Then Bn of T converges to B of T. Because of uniform convergence on compactor.
The complement of omega has very small harmonic measure, right, from 0.
Right. So when you approach this entire thing in terms of GT, this entire thing is a very tiny region. So, okay. So sorry, maybe let me hear again. What did you say?
So since you're starting, if you start a Brownian motion from 0, it won't hit the complement. It will hit the complement with very low probability.
Right. That's correct. So in terms of conformal maps, what it is, so if you, let's say you look at GT a little before that time T. Okay, let's say, okay, somehow it magically gave me this. Okay, so let's say GT is like this. You are almost hitting, but not yet. So how does this map look? What does it map like? What you are saying translates in this to this entire region outside of omega. This entire region omega complement will get mapped to a very tiny region. So the omega complement, I mean all the parts here, GT is almost a constant in all this. That is related to what you are saying, that from point of view of Brownian motion, this is not nothing actually. This doesn't exist. This is as good as this small slit, in other words. So that's why this GT converges to G uniformly on compact sets. This region, which looks big in Euclidean geometry, is in conformal sense small. So this gives the convergence of coefficients. In other words, what he got is that these slit mappings are dense in the space of all conformal maps, just roughly speaking. And so the certain problems on coefficients of conformal maps, he could approach via this differential equation. Okay, so, well, what I mean by that is, so, yeah, what do I mean by that? Yeah, let me, so, I mean, do people want to hear this further motivation, or shall I just go back to the?
No, go ahead. It's wonderful.
Okay. So what is this?
Unless some people are impatient. I mean, I'm already...
Okay, one is taken as yes, it's okay. So, okay, so let me do it. So let me tell you what is the coefficient problem that can be solved like this. So look at the maps. Now I don't look at GT, but let me look at FT. Okay, so let's look at FT of Z. We know that it starts with what is FT of Z? It is the, oh, actually, sorry, I made a wrong statement. GT dash of 0, it is mapping from a smaller region to a larger region, right? So its derivative is bigger than 1. Is it correct? So, yeah, so this should be actually e to the t, I think. I'm sorry about that. So GT dash of 0 is e to the minus t. It is FT dash of 0, which is, FT is the map that maps the disk to a subregion of the disk. Therefore, its derivative is less than 1 by Schwarz lemma. Sorry about that. Just but that doesn't change any of the other things I said. It's just it should have been e to the t, and FT dash of 0 is e to the minus t. So ft of z, how does it look? Its power series looks like e to the minus t times, let's just write it as z plus a2 of t z square plus z cube and so on. So this is how ft of z looks. And we now know Lohner, because of Lohner's differential equation, we have this entire differential equation that is helping us. Okay, so what happens when we bring that in? Okay, let's calculate all the things that are there. ft dot of z is, if I can differentiate here and I get minus e to the minus t, z plus a2 of t, z square plus dot dot dot, or I can differentiate things here that will give me e to the minus t. Here when I differentiate, I get a2 dot of t, z square plus dot dot dot. Okay, that is one. I also need ft dash of z. Let me write that. Ft dash of z, you just differentiate inside. You get 1 plus a2 of t into 2z plus blah blah blah. Okay, what else do I have? I have lambda t plus z over lambda t minus z. Which is, you can write it as 1 plus z over 1 plus lambda over z over 1 minus lambda over z. I think so, or maybe I want to write as z over lambda. Sorry. Yeah, 1 plus z over lambda of t over 1 minus z over lambda of t, and you can now expand it in power series of z over lambda of t. So that comes out as 1 plus 2 times z over lambda of t plus something by z square over lambda of t squared plus dot dot dot. Okay, we have this whole thing. So now you have this equation, right? So equate coefficients. What do you get? Okay, so if you now have the differential equation, let's try to equate the coefficients and see what you get. So what we have on this side is, so ft dot of z, it is e to the minus t. E to the minus t is common everywhere. Maybe I just delete that. Okay, maybe I will delete it in a moment. E to the minus t, and then left side we have ft dot of z. So I have z here. So let me also pull out a z, z e to the minus t. Then I'm left with minus 1, that is coming from this minus 1. And then the coefficient of z, because I have pulled out z square, I have pulled out 1z. So I'm left with minus a2 plus a2 dot. Plus dot dot dot. Okay. This is equal to what do I have on the other side? Minus z times ft dash of z. Okay, so let's write minus z into ft dash of z will have an e to the minus t. And then I have this whole thing, 1 plus a2 into 2z plus dot dot dot. And then I also multiply by this one, 1 plus 2z over lambda plus dot dot dot. Okay, so let's cancel z e to the minus t. What we are left with is minus 1 plus z into a2 dot of t. I mean, I'm suppressing the t for the moment, plus dot 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 is equal to, to cancel all this, what you are left with is first term is minus 1. Okay, better be, it's minus 1 on this side. What's the coefficient of z on this side? So this is gone. So coefficient of z is, I get 2a2 over, 2a2 plus 2 over lambda. Okay, the whole thing with a negative, right? The whole thing with a negative. I hope the signs are correct. Otherwise, I will just have to say exercise and leave it. Okay. So what do you get? You get a2 dot minus a2, for example, is equal to minus 2a2 plus 2 over lambda. Okay, A2 is a function of t, lambda is a function of t. Okay, so now that is, so that means A2 dot of t, let's write A2 dot of t is equal to minus A2 of t. Let's write A2 dot of t plus A2 of t is equal to, sorry, this is also a minus 2 over lambda of t. Okay, so if you are awake when they were doing integrating factors in differential equations course, you will know you multiply by e to the t. So then this is becomes the e to the t A2 of t coefficient derivative, right? So that is actually equal to minus 2 times e to the, sorry, should I write e to the t or e to the t over lambda of t. Or in other words, e to the t A2 of t is, you integrate this 0 to t to e to the s over lambda of s ds. You get something. It's not clear what you got, but now this is amazing because what you get from here is that if you look at absolute value of A2 of t is less than equal to, let me transfer the e to the minus t to the other side, and you get that actually, sorry, so something is wrong actually. Okay, I get this, but now I'm, yeah, lambda is e to the minus t, and then here you get, if you put the absolute values inside, you get 2 e to the s ds, which is something like 2 e to the minus t e to the t minus 1. So you see it is less than 2. Right, so you get this fact that A2 of t is less than 2. Actually, I am slightly worried because the coefficient is, okay, this is correct. Okay, so the derivative is this. So A2 of t is less than 2. So for all these type of maps, right? So what you got is the big conclusion is A2 of t is less than equal to 2. But what does it mean? It means that if I take any conformal map from the disk to a slit domain, then if I normalize the first derivative to be 1, then the second derivative is at most 1. Okay, so this says that if f is from the disk to a slit domain Riemann map such that f of z, if I had normalized it so that the derivative is 1, then the coefficient A2 is at most 2. Okay, and now we argued that slit domains are dense in the set of all conformal maps, right, to any bounded domain. So, and consequently to all domains. So this implies that it is true for all univalent maps. So what it means is just it is, I don't put any condition, any omega, simply connected, and it's a Riemann map where 0 goes to f dash of, let's say, without loss of generality, say 0 goes to 0 and f dash of 0 is 1, then the second coefficient is less than or equal to 2. Okay. So some of you may have seen this. This is called, this is actually there in, so you'll find it in, so under the name area theorem. So you can see it even in Rudin's real and complex analysis, not this proof. Not this proof, it's usually proved by other methods. So, but this Lohner's method gives you a way to approach this. And the question was the next one actually. So Lohner was not proving this, but since that would take more time, I didn't want to do that. So what Lohner did was, you just have to follow the next coefficient. I just stayed with the second coefficient here, first coefficient. You also keep to the second coefficient. Means you see what happens to that. Followed coefficient of z square in this equation in this here, in this expansion, you also follow the coefficient of z square and prove A3 is less than or equal to 3. So that was part of Bieber-Bach conjecture. So the Bieber-Bach conjecture was that an is less than or equal to n for all n. It's now known. This is Dibban just proved it. So an less than or equal to n for all n. So Lovner developed this entire machinery to prove A3 less than or equal to 3. It's actually not far from here. You just have to follow the next coefficient, but there is a little bit of manipulation involved. If you want to see a proof written down, you can look at Alpho's book, Conformal Invariants. This is a very beautiful book. There is a chapter on Lovner where he derives the A3 less than or equal to 3. So this was the motivation of Lovner, okay, at length actually. So much more than any questions, comments? Actually, I had a question comment after this. Last time we were running some SLE seminar. So this, as I said, all this was done. And now this boundary normalization, nobody did. So a question I asked somebody, but they also didn't know. So this person knows a lot, but he said that he doesn't know. Is that what, so if you look at conformal maps, not like this, not univalent maps, not like this, but univalent maps normalized at the infinity. Let's say univalent maps from upper half plane into subdomains of the upper half plane. Those would be like inverse of this GT. So what is the corresponding coefficient problem? And does this Lovner differential equation solve at least the third one or whatever there? I don't know what is the coefficient problem there. Analogous to the Bieber-Bach, there must be something. Okay, I didn't spend enough time to work it out. But if somebody is interested, it might be fun to work it out.
Yeah, one other thing, Manju. What about, say, positive degree maps? So these are univalent.
Okay.
But
what is positive degree map? I don't know. Sorry.
Meaning, say degree 2 map. So every generic number of pre-images of a point is 2.
Oh, I see.
So say for example, disk z goes to z square.
Yeah.
So presumably there should be versions of this where the slit splits into more than one slit.
Okay, there are two. One is when there is a coefficient problem. Oh, is that all you are asking about the method?
Or so what I'm asking is there an analogous? Yeah. So basically.
No, I have no idea actually.
Okay.
I have not seen one such.
Okay, fine. Yeah, no, one has to have problem first, and then, yeah. Anyway.
There is something people studied multiple SLE, but that's not related to this, I think, which is a bunch of curves are going inward.
Right.
But that's about multiple interfaces in statistics.
Yeah,
sort of. You have, you can, instead of one U of t, you can run a measure on the real line. Then you can get complicated going sets KT.
Correct. So essentially, what you're doing is basically say put weights at say finitely many points, and then you start running curves inwards, and then do the uniformization. Is that what you're saying?
Or backwards. I was saying it backwards, but so let's say instead of this, what is it I want to say? So let's say if you consider what I was saying was this, that if you look at x dot of t is, let us say, 2 over, it may be a different coefficient, x of t minus u of t plus 2 over x of t minus v of t, let's say, just in the simplest case, where let's say u is a curve that starts here and v is a curve that starts here. If you solve this, then also you will get some k sub t, right? That will probably, in the beginning at least, it will look like this, I think. it will have one curve going from U0, one curve going from B0, I think. So maybe Shubhajit knows. I mean, so this is what I
Yeah,
was.
so it's called like this SLE with the force points, right? I think, yeah.
It will have multiple, you can
So,
make
yeah.
multiple curves by things like this. And so, yeah, that has some uses. I don't know anything about that either, but.
Well, these are actually used, I mean, have been heavily used, for example, to construct, make sense of level lines of GFF in dimensions and things like
I
that.
see.
So if you, so, you know, the classic Sheffield Schramm work. So what you do is that you put two boundary condition on both sides, like one plus minus lambda. There you get one interface.
Yeah.
But what you can do, you can take piecewise constant boundary conditions also. Then multiple interfaces will emerge, which will be described by kind of equations like that.
Okay, okay. And they will be defined by SLE like this, or
yes, something like that. So I don't know exact definition I have to recall, but this is a little, yeah. So essentially, you have this sum on the right hand side. You have a sum of this different driving functions, like.
Okay.
So by the way, I just had a small historical question. So this Leibniz couldn't be pushed beyond 3 or what?
No, it doesn't give. I haven't checked why, but it apparently doesn't give 4. Already 3, yeah. So maybe it doesn't close properly or something. I don't know what the issue is. But it was, I mean, but I have not read this. Apparently, Debranches used the Lohner's work also, but I'm not sure in what way and so on. But it's not this, just following the coefficients here apparently stops at 3.
I see.
Okay.
Manju, you said something just before this discussion. You were saying something about coefficient problem for the other class of maps. What was your question?
Yeah.
You said something, but yeah.
Yeah, right, exactly. So this, for example, if we get, like we said here, these slit maps are done. So suppose for all these maps which map a disk to a slit map inside the disk, if we have some inequality, that will extend to a wide class of things, right? So what I was asking is, if I look at maps like maps FT2 from H2, okay, and what is there a coefficient problem for at infinity? So you write ft of z as z plus some a of t, a1 of t over z plus with this normalization.
Oh, I see. So there's this analogous question where people look at univalent maps from the exterior disk to the plane.
Okay.
And this class, like this class, you're talking about the class S, right? The univalent maps normalized on the unit disk.
Right.
This class is called, not this class, but the class of univalent maps defined on the exterior of the unit disk to the complex plane. This is called class sigma, and this has a similar normalization as we have written down. And for that, it's actually not known because the area theorem is stated for exactly those maps, right? If you take a, right? Yeah. So univalent on the exterior disk to the plane, and then you have the summation n times absolute value an square is less than 1, right?
Okay.
So that means your an square or an grows at most as 1 over square root of n.
Okay.
But nothing, something better is known, but the exact area the exact coefficient problem is still not solved for that class of maps.
I see. So the second coefficient in the two things are basically the same, but
right.
Oh, I see. The higher ones are not known. Okay.
The higher ones are not. Yeah.
I see. No conjecture, or there is a precise conjecture? Or...
There's no precise conjecture. I think the precise, I mean, all that is known is 1 over square root of n is too bad. Something like 1 over some other exponent is known, but it's known that it's not sharp. So there's no decent conjecture either. In this book by Durin on univalent function, there is a discussion on these class of maps.
I see. Okay. Okay.
Sorry, I missed one part in the discussion. Sorry. This coefficient, so what normalization you're talking about again? So for example,
I think it is functions
that's
of the disk.
That should be the capacity, right? Okay.
Is it this? I mean, so just to be.
Yes. To the whole plane. To the whole plane.
Oh, sorry. To the. No. Sorry. Yeah. but univalent here.
Univalent here.
Okay. And you look at the coefficients at infinity of this.
Yeah, so you write it in the usual Lorentz series the way you wrote it. Yeah.
Okay.
It's actually tangent to identity. So A naught has, I mean, you can just
make it 0.
do any affine map. That can be 0. That you can normalize to be 0. And then your map starts with, it's tangent to identity at infinity. So it's Z plus 1 over Z plus A2 over.
Okay, this will make it to be 1, and then ask about
No. I'm saying no, that you don't know, but you want to say that infinity goes to infinity. So
right.
Z, so the Lorentz series starts with Z plus A1 over Z plus
there is
A2
a
over
Z term,
Z
right?
squared, etc.
Oh, sorry, actually, it goes to infinity, Sorry, yeah, I forgot that. So
sorry, Shubhra,
Yeah,
so again, can you repeat, like, what is the conjecture again? What is believed to be AN is asymptotic to what?
It's not known. It's not known. Mod of N
okay,
is
but
at
no
most
conjecture,
1 over
no
square root of N. No, there is no precise conjecture.
No, so 1 over square root of N is from area theorem, right? I think you can
From area theorem, yeah. And then people have improved that. In fact, Smirnov and other people worked on this, but there is no. So the problem is that in the case of the of class S, you know that the maximal or the optimal function is the Kobe function that attains all these bounds. In this class of function, it's not known what is the right.
Sorry, I interrupted. Go ahead.
No, sorry. Yeah. So in this case, it's not known what is the right function to look at that's gonna maximize all the. If there is any function at all that maximizes all the coefficients simultaneously, that's not even known. Okay.
Yeah. No, that reminded me. I didn't mention it, but this thing is optimal. So this is exactly the point. So you end by a single function. So if you take Z plus 2Z plus 3Z square plus so on, it maps the disk to the, I think, complex plane minus a slit like this up to -2 or something like that. And that achieves all the coefficients equality actually. Yeah. Okay, this is an interesting question. So what I was asking, I just wondered whether there is some problem like this. I have no idea whether it's a meaningful one, but for these type of maps, yeah. Okay. Any other comments or questions?
I have one question, which is, how does the Lohner equation change if you reparameterize UT?
So the way, I mean, that is okay. At least in this case, I can say quite simply, you will just get another term here. So here it is normalized. Let's put it here. So I said GT of Z is 80. If you don't normalize 80 to 2t, so then here you will just get GT dot of Z will be 2 times A dot of t over GT of Z minus U. We'll just get this.
Okay, I see. And if you scale t, say in UT?
That I will come to. So we can see what happens if you scale. If you just scale, I can't say, but if you, I will come to this point. Yeah, so it's a good question. So there are a couple of ones. If you know for U what happens for related curves, we can say that. So maybe I mention it now. So now I come back to my original one. Unless there are some other questions, we'll be happy to take. So we'll go back to this equation. GT dot of Z is with G0 of Z equal to Z in the upper half. So related to the questions you asked, one is, I mean, one simple one is, let's take a different curve. Let's call it U tilde of t. Let's take the curve beyond a point, U of t plus some capital T, and I want to start at the origin. So let me subtract U of capital T. So if I do this, then what is the corresponding thing? What happens to the linear differential equation? It is actually easy to work out. The G tilde, the corresponding G tilde T, the solutions with U tilde. What I mean, I hope it's clear, right? When I write G tilde T of Z, it is whatever is satisfying this with
Right.
tilde. Right. So that will be just G T plus T of GT inverse Z. Maybe we will have to subtract a U sub T, I think. Let me just see. CO goes to UT. Yeah, something like this. So it's just this. And you can ask what happens to the K of T. K tilde T. K tilde T will be just, so what is K tilde T? It was the part that was absorbed, right? So it is the K tilde T is those Z for which the flow line met UT before time T. So that will be just something like you take K T plus T, that is the originally what was being absorbed. And then you just K T plus T and then use, okay.
So this kind of thing will lead you later, I think, to domain Markov property in a sense.
Yeah,
right?
exactly. Yes. So sorry, I got confused. What is it that will, so this is up to time T, and then I want to see what is this, right? So that is, you just have to map it by G sub T, right? So I think it will be just G sub T of this. But again, it will be shifted by U sub T or something like that. So you can just check whether it satisfies the differential equation and this. Okay, I will. There could be small mistakes here, but you'll be able to figure out. Another one, which is the one you asked about scaling, that is also we can do. So suppose I define U hat of T is U of, let's say, A times T. A is some positive number. But then I don't know. I mean, so if you do that, it's actually very complicated. If you do U of AT over square root A, then we can tell what it is. I mean, if you could do that, I mean, you'll see there is good reason. If I just scale it, it's not possible to tell. So G hat T of Z in this case will turn out to be just, I think, G sub AT of Z over square root A or something like that. And K hat T, the corresponding curve, will also be just something like that, KAT over square root A. So this is what happens under scaling. But if you don't put this one, then it's, no, we don't know. I mean, that's the whole point. It's completely different curve, actually. We'll see in a moment. Yeah. So one more example, maybe this is a prime example. Let me give this example, just extending the last one to a bit. So one more example, because we did only the case when UT is 0. UT equal to 0, then it's the vertical slit that is going. So, okay, so I mean, what we pay attention to this KT. I mean, this going hulls, going sets KT are very important. So one more example. So you might be tempted to look at, okay, next simplest, let's take a linear curve, CT. I have no idea what happens. So we take C times square root of T. Then we can say what it is. C times square root of T. What happens to this? Okay, so I actually will not solve it, but I will tell you the answer. But one thing you can see, if you do this U hat here with the U hat of T, what is it? It is C times square root of AT divided by square root of A, right? I mean, if I do this transformation here for this particular curve, then you get back U. This is why that square root works. Square root is good. U hat is actually same as U. So what this is telling is it's some k hat. So this k hat t. So what this will show you is that k hat t is actually, or rather, so it shows that k hat t is actually kt, because u hat is same as u. So k hat t should be just kt, right? But we also know it is this. So what that implies is that, what this implies is that kat by square root a is actually same as kt, the entire collection. So what you get is kt is actually, put t equal to 1, a equal to 1. So kt is square root a times k1. So this is some set which is going, sorry, square root t times square root t times k1. So whatever this set is kt, these kts are going in a homothetic or whatever, but at the rate square root t, not linear in t, but it is just the same shape being expanded. What is that shape? This I won't solve for you, but I will just tell you that this k1 is just, what is k1? If I tell you what is k1, then you know what is kt for any t, right? So what is k1? K1 is actually a straight line segment. Okay, so this is k1, and this number is some r, let's say e to the I. I will write down the formula. I have it written down here. So let me write it like this. I'll just write. It's not important to know the formulas, but let me just look it up and write here. So it is it is both everything depends on the number c. Yeah, what is this? R is something like, so where R is, there is some formula like this: alpha over 1 minus alpha to the power of alpha minus half. You don't need to know any of this. The angle, this angle, so the angle is determined by this, right? So the angle is also determined by the constant. 2 into, okay, let me just see, is the square root. Okay, so it looks to be like something like this. So this is how, so alpha you can solve in terms of c, and then r is something, it doesn't matter what it is some slit of a particular length, and then this is being, so kt will be just the same thing expanded at the rate of square root t. Okay, so how do you solve it? It's actually if you know Schwarz-Christoffel transformation, this is a polygonal domain. So you have a straight line, another straight line, another straight line, another straight line. There's 4 straight lines. It's a Schwarz-Christoffel map. You can one can solve it explicitly, and you find that this is actually giving you something like this. So the Schwarz-Christoffel map is also some power z to the alpha, and z something is there. Okay, I haven't. Do I know what it is? Okay, I haven't written it down, but it is it has some powers of z with these fractional powers. Whatever it is, I will not write it. But the point is, one thing that you notice is that if c is positive, then what does that mean? Alpha is bigger than half. So this angle is also positive. So pi into 1 minus alpha belongs to 0 and pi by 2. So it's going, if the curve ut is going to the right, then this slit is also bent to the right. And if c is negative, then this angle is in minus pi to pi by 2. Pi by 2 to pi. It will be this way. If c is negative, then it will be going in this direction. So I think this Sabyasachi asked earlier about the symmetry of the earlier one. This shows how if u goes to the right, this also bends to the right, and if you go to the left, it also bends to the left. So this is an important example which actually gives considerable understanding, at least to me. And let me say another question Balarka asked. So if you just simply scale it, you see that the very angle changes depending on c. Okay, so it's not actually something simple. So when you change this constant, the angle at which it bends changes. As c goes to infinity, this angle goes all the way to 0. When c is 0, this is going vertically. When C goes to plus infinity, it's almost like something sleeping like this. If C is minus infinity, it will be sleeping to the left. This is very much important for us. It's very related to the parameter in the SLE thing. So we'll come to that. Okay, but already it's 4:20. I should stop here. So maybe we'll do SLE. I mean, next thing is to put U of t to be Brownian motion. Okay, so that will be SLE. What we get is SLE. Okay. Maybe I should stop here.
Is to send us the notes.
Yeah. Please.
I can, so there is a way to share this also. I will find how to share the OneNote.
Great. Thanks.
Yeah, I will just share it with Mahan, then he can just send it around.
Yeah, or you can, I mean, there's this thing where I send out this thing to everybody saying that your talk is on such and such date. Just reply to all there. And
Okay, then I can send it there. Yeah, I can send it there. Sure.
Thanks.
Okay.
Thanks, Manju. Okay. If no,
Thank you, Manju.
are there any other